Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome to yet another NL Math Man Math Help stream here on day 62. Boy. Yeah, we're in the home stretch now, I suppose. Boy. Um, yeah, over here to the side now we've got a nice picture of the Aggies again, right out in the sunshine. Because, they are my sunshine. My only sunshine. Um, Below us today, we've got the topics that we'll be getting to. I'm going to talk a bit about um, some physics topics here today. We're going to introduce distance versus displacement. Well, introduce. I mean, I talked about those yesterday, but I did kind of just ramble, sort of. So today I'll actually discuss those, like, you know, in with with more reasonable examples, I suppose, maybe a bit more detail. We'll go over speed versus velocity, and then I'll just do some questions from the recap to Physics 1104. Because Troy, I know you're getting on to that nearly to do that test, right? And letting some students clue up tests on Friday here now, just so we can get them out of the way before the summer break, right? Because now, as of tomorrow, right? After that, it'll be done for the summer. You don't want to have to get most of a course done and then leave it for 2 months and come back and write the exam in it. That would suck, right? That'd be like doing the course twice almost, right? Because you're not going to remember a whole lot. You're going to have to do loads of studying when you come back to it. So it's definitely best to get this out of the way here now, right? Um, yeah, then after I get through that, I'm going to do a bit of Venn diagrams recap. Now, Calais, that is for tests that you finished today. I gather you're not going to be starting on your next course tomorrow, seeing you finished one course today. Maybe one day we can take off. I don't know. I don't know. Am I allowed to say that? Is the teacher allowed to tell students to take one day off? I don't know. Normally our like last Friday before we left would be a half day with a lot of stuff off anyway, right? So in this case, I think I'm okay with going ahead and saying maybe if you finished an exam today and finished a course, don't and you're not staying in Kenmount over the summer. If you're taking the summer off, then yeah, maybe tomorrow you can just sort of take it easy for a little, right? But anyway, yes, I am going to. I'm just going to get straight into the work today. Not really much banter about anything at all. I mean, I guess there is the Atlantic bubble. I suppose I could talk about that, but I don't know what much there is to say about that. I mean, my time on the internet commenting about COVID-19 and social distancing is coming to a close rapidly. Maybe I'll have some coherent thoughts on that tomorrow. But I mean, it's good to see. It's good to see the provinces coming together and opening back up. Um, and all the Atlantic provinces, all four of us, do have like very few active cases, and yeah, we're this corner of the world is doing exceptionally well, I think, at combating COVID-19. Now, at the same time, like, boy, anybody who's paying attention worldwide and at least continent wide might be a little, can be forgiven maybe for having some renewed trepidation about the pandemic, seeing, the day after day case numbers in the United States are the highest they've ever been since the beginning of the pandemic, right? But far be it from me to comment on, the way my neighbors should be handling something. But boy, oh boy, viruses don't necessarily respect national borders, right? Like, you know. Anyway, it's not going to be a politics and COVID-19 talk stream. But hey, at least in local news, the Atlantic province is opening back up. Is it's a bit of a breath of fresh air in a sense, especially with Newfoundland having no active cases. I think PEI has no active cases they've had for a while, and I believe Nova Scotia and New Brunswick have very few. So yeah, we're doing all right over here on this corner of the continent. You know, our combined like not even 2 million people, I don't think, right? Our combined like 1.7 million or something in Atlantic Canada. We're doing okay. Anyway, let's do some physics. So over here now, uh, yeah, this is some of the pages from the book, Troy, that you were doing for position time graphs. Now, yeah, I call them displacement time graphs. I think it's yeah, six of one, half dozen of the other, basically. right? But a position time graph, I'm not going to read down through all the pages on the text or anything like that, but a position time graph is distinct from a distance time graph, and in a way that maybe wouldn't be apparent just from the name, right? Because sometimes when you hear distance, you think, well, it's the distance I am away from something, right? So if I move forward, I'm increasing my distance away, but if I move back, I'm decreasing my distance. But actually, no, no. I mean, in English, in the language, we could make sense like in your head, but in the actual physics terms that we use in physics courses, that ain't how it works. Distance always increases. So if you look over here on the next page, and sorry, this one's a little bit slanted, but it's just because I feel like I explained before, I don't actually have digital versions of this textbook. If we zoom on in here, right, we see this is a comparison now between the two. Actually, let me keep both of them up on the page at once so we can see both. There we go. That's better. So trip to the video store, right? That's a quaint notion, isn't it? Video store. What in the world's a video store? That's like that's like social archaeology, right? We've unearthed an ancient blockbuster. We think that in prehistoric times, cavemen used to travel to this store to rent pieces of film with rolled up film that had media on them. And they would put them in a projector system that would sort of send light through it and shine it on a wall, or even project it on a self-contained screen. How quaint! They didn't the time before streaming media. Trip to the video store. My goodness. Anyway. Um, so this one here is a distance time graph, right? And you'll notice that the slopes are either positive or zero, right? Technically, well, not even technically. In these courses, you will never see a negative slope on a distance time graph. And why is that? Well, it's because distance is a scalar quantity, right? Which is to say a quantity without direction. It has only a magnitude. In a sense, you can think of distance as sort of the absolute value of displacement, right? In that it's always positive. Let me label the sheet. Okay, so I'm going to start off with a few definitions, and this is going to overlap a bit with some of the questions that I had on the list to do for later, and we'll skip those questions when we get there. But distance is only positive or zero. Well, I mean, okay, let me zoom out of touch with my dock cam here. I'm apparently zoomed in a bit far. We're not quite getting the full page. All right. I think our wobbling has stopped. Okay. So I know technically zero is a positive number, right? Kind of, but for this instance, I will specify the difference, right? So distance is either positive or zero. So either you're moving, in which case your distance is positive, or you're stopped, in which case your distance is zero. That's it. That's the only possible measure. I mean, distance is still a relatively useful scalar quantity, right? Because imagine being on a treadmill or something like that. Well, a treadmill is maybe a poor example because you're not really getting distance in a sense, but it's still like it's kind of an interesting example, right? Because you're kind of getting distance because you're running, right? But you're actually not. Your displacement is zero the whole time, right? Because your position is actually not changing. Oh, that's maybe a poor example, right? Because kind of your distance is zero too, although your distance over the tread of the treadmill is not zero, right? But your distance sort of like in the room kind of is. So that one is a bit of a weird example. But say you're going for a hike, right? And say the hike winds around in a circle or something like that, or even makes like like an S or an ampersand or a figure eight or something like that, right? Your distance that you go, well, it's still really relevant to know. Like maybe I hiked 4 kilometers, but this 4 kilometer hike was a loop. So if you graphed your position or your displacement, you would end up with zero, right? Displacement, I'm going to mention that here. Displacement is a vector quantity. Right now, again, like I was saying yesterday, I don't like introducing things part way, although I will kind of do that here. Displacement doesn't simply have a positive or negative component. Displacement actually, um, well, it has two dimensions or three dimensions really, but and as we'll see here now in a second, I'm going to do an example of sort of a two-dimensional displacement, even though it's not it's not what we're getting to right now. I think you'll see that it explains the concept pretty well, right? So distance is kind of one-dimensional, is sort of what I'm saying, right? Because distance is always just how far you go forward, and whether you turn left or turn right, distance don't care, right? It doesn't matter at all. For displacement, if you turn left or turn right, it does indeed matter. And we will see later on that, say, on a map, like if we're looking at a two-dimensional thing where you're just moving around on like a just sort of moving in area, right? There will be you can have an east-west and a north-south component of displacement, right? Whereas distance will not have that. So position is sort of how we graph displacement. And I say position is in one dimension, meaning it's how far you are away from the starting position. What do I mean there exactly? Position is has one dimension, whereas displacement has multiple dimensions. Well, if we look over here, back to our graphs, right? Well, these both have a time dimension. I should say one. I mean, let's be extremely pedantic. Has one spatial dimension. All right. Excuse me. I yeah, I like to be extremely precise here. Um, position has one spatial dimension, meaning either it's basically your straight line, the direct distance you are from the starting position is its starting location, I should say, is your position. Not to use the same word to mean two different things in the same sentence. Because what do I mean by that? Well, we look over here, right? Look at both of these graphs. On the side, all it says is distance or position. And if it says meters, what is that? Meters north, right? So that's what it's saying. We're only concerned about the meters we are north. So that's one dimension, right? We could also look at position in the sense of just how far you are away from something. So, for example, like if you were rotating, like in a circle, right, and staying equidistant from a point, then your position could be staying constant, but you're still moving. But your position, as far as your position, right, the distance you are away from something is not changing, right? Your displacement is changing in a sense because the north, south, east, west sort of quantity of your displacement is changing, right? But the distance and the distance is changing because you're actually moving. Anyway, it is. I'm really sort of slicing this hair into multiple sections here now. It's not just being split; it's being like carved up like a pizza, right? But my point is, there is one spatial dimension here. You see this, right? Position just has a distance you are away from something, But it shows here, right, that the person goes to the store in this point, stays at the store for this point, and then returns back. So the distance or the position, sorry, the position that they're in relative to the video store, it starts at 0 because they're at their beginning point. It goes to 10, 10, 10, what is that? 10 meters? Yeah, it just says 10 meters, huh? Well, that's a pretty close. That's a that video store is pretty close. Apparently, it's 10 meters away. Boy, all right. Um, maybe that's supposed to be kilometers, and I'm just not zoomed in far enough to see it. Do my eyes deceive me? No, it says meters. Okay, sure. That video store is really close by. Whatever. Um, so he goes 10 meters away in 10 minutes. This is a very slow walk. That's gotta be supposed to be kilometers, right? And he's driving? Whatever. Physics textbooks don't matter. The specifics of the example maybe don't hold up under scrutiny. I guess they weren't expecting someone to blather on about this for a solid 15 minutes on a live stream. Although, I guess teachers talk about this stuff all the time. Whatever. Whatever. Um, right? But he goes 10 meters away, stays at 10 meters away for 20 minutes, and then returns back. Right? But the distance just increases each time because it's just like how far you have walked. Right? Like if you were wearing a pedometer and it was telling you the number of steps, it would be telling you distance. Right? But if after you did your full trip, you looked on Google Maps and you just saw how far you are away from where you started, well, that's going to tell you your position, or rather your displacement. Now, what do I mean when I say displacement has two dimensions? Right? I do want to show a little bit about what I mean there. We don't really get onto it in these examples. I do have these other pages here. And Troy, I think I answered your question about this one decently. Let me know if you're still a bit confused about here, but this one here, it is indeed the book's fault. These two numbers needed to have been switched, but they did do the working correctly, because remember, it's of course d2 minus d1 over t2 minus t1, so they've got them in the right spot down here. They just didn't have them in the right spot here. But say, for example, we had a situation where I'm not going to use graph paper for this one, where we started here, say on this dot that I accidentally made on the paper that was extremely dark from previously. Say we started here and we went. Let me get myself a ruler. Say we went 4 kilometers north, like this, and then we went 3 kilometers east, like so, right? So that's going to be 4n and 3 east, like so. What is our resulting displacement? Well, what's our distance? Let's do that one first. So our distance here is just going to be 3 plus 4 equals 7. I meant for that to be kilometers. That's just going to be 7 kilometers because that's just how far we've traveled. But how are we going to find our displacement? Well, our displacement, of course, is going to be between here and here, like so. Right? The blue line there, that's going to be our displacement. So how are we going to find that blue line? Well, I'll tell you how we're going to find that blue line. It's going to be 3 squared plus displacement squared is going to be 3 squared plus 4 squared. We're actually just going to use Pythagorean theorem here, right? Because we're concerned about from here to here. So, of course, now displacement squared is going to be 9 plus 16. Displacement squared is going to be 25. So the displacement is going to be 5. Then we would also need to find the direction of it, right? If we wanted to be totally accurate about this, we would need to find the direction. So there we would actually use we would use sine or cosine to find this one, right? Because we would also need to find this angle here to get the total displacement, right? So then what we would do is we could do tan theta, because remember tan is equal to opposite over adjacent, right? So tan of 3 over 4, because it's opposite over adjacent. So theta is equal to the inverse tan of 3 over 4. So theta is going to be inverse tan of 0.75, 36.9. So what we would call the total displacement, right, or the final displacement, it's going to be 7 km at 36.9 degrees east of north, right? And that's just what we would call the entire displacement here if we had just this sort of simple situation. So this is not what we're doing right here, but I think you will see pretty clearly that all this math is stuff that you have already done, right? And that's fairly simple Pythagorean theorem and trigonometry that we use here to figure this out. But you'll see that the resulting displacement, oh, not 7 kilometers, my goodness. What am I doing? 5 kilometers. We found that to be 5, yes. 5 kilometers at about 37 degrees east of north. Right? That's just the way that we would calculate displacement. You'll see that in your very next physics course, I believe. So it's not like this is a mega preview or something like that for you. But, and I hope that might help explain a little bit more what we're talking about in this course when I say that sort of displacement has 2 dimensions and it's a vector quantity, whereas distance has 1 dimension and it's a scalar quantity, right? And the position is kind of like a 1-dimensional analog for displacement, right? Because say if we're looking at this one here, right? If we looked at the position, well, the position in the end is just going to be 5 kilometers. It's not necessarily going to be 5 kilometers with this degree over here, right? But this is what makes it a vector quantity, because a vector has an angle like this, right? Whereas the distance, scalar quantity, does not. It is simply 7 kilometers. Okay, so Troy, let's go do a few questions off the review section for this course. Do want to do a few of these questions here. I'm not going to go down through a whole ton of these, but I do want to make sure that you're sort of understanding how you complete these guys before you go on and do your final. All right, so I'm going to be looking at page, what is this? Page 410? Page 490. No, page 490. So you're tasked with doing quite a few of these. I'm just going to pick several of them to do. Excuse me. Which quantities must be measured to determine the average speed of an object? Well, speed is just the rate of change of distance equals the speed, right? So it's distance and time, right? And what's 1b? The average velocity of an object. Now remember, velocity is a bit different, right? Velocity is the rate of change of displacement, right? Or we could say the rate of change of position. I'll say the rate of change of displacement. Displacement and time here for that guy. Right? Number 2, for each of the following types of motion, state what remains. Now some of these questions are a bit silly, to be honest. I'm going to skip a few of these, but let's see. For each of the following types of motion, state what remains the same during each time interval. Constant speed. Well, the speed stays the same, right? Like, come on, what in the world are these questions? I mean, the rate of change of position, or the rate of change of distance stays the same. Constant velocity, the rate of change of displacement stays the same. Constant acceleration, the rate of change of either speed or velocity. Generally, we say velocity the rate of change of velocity. Some of these definition ones are a bit silly. Number three, yeah, let's do number three because this is kind of similar to the sort of things that you would see on a test, right? Um, Match the terms those with the following descriptions: the length along a path, well, that is of course distance, right? Displacement in a given time, well, that's what we call velocity. Easy. C, location relative to a reference point. Location relative to a reference point. Well, they haven't really. Well, that's going to have to be position, right? Yes, that would definitely be position. Yes, because it's your reference point for position is generally the start of your motion, right? It's not always. It could be somewhere partway through. They could say, okay, what's your position relative to where you were halfway through this walk, right? But yes, that is position there. Change in velocity in a given time. Well, change in velocity is acceleration. Like I mentioned before, it's acceleration, not deceleration. Deceleration is kind of a fake idea. It's just negative acceleration, right? Or a decreasing. Anyway, so E, change in position. Change in position is displacement, whereas the rate of change of position is velocity. And then F, the distance in a given time. Well, distance over time gives us speed. There we go, right? That's all there is to that guy. Distinguish between number four. Okay, let's. I'll just talk about number four a little bit because I've already sort of talked about this one already. It's the difference between constant speed and average speed. I mean, that's not hard to figure out, is it? Right? Like, constant speed means you're moving at the same speed, the exact same speed for a given amount of time. Average speed is simply we see how fast you like how long it took you to take Jesus, how long it took you to get somewhere, and then we just figure out what the average speed would be, right? For example, say it takes you, I don't know, say it takes you 3 hours to drive 400 kilometers. Actually, you're moving, you're flying clip there. 3 hours to drive 240 kilometers, right? So you would just do 240 divide by 3, and your average speed would be 80. Does that mean your constant speed was 80? Of course it doesn't. It doesn't necessarily mean that you were doing exactly 80 the whole time. If it took you 3 hours to drive 240 road miles or kilometers, then that's your average speed. But your actual speed was probably not constant very often, right? Because, you were stuck behind somebody doing 60 in an 80 zone. Maybe you were speeding a bit to catch up and you jammed on your brakes when you saw a cop. I don't know, right? Like there'll be loads of fluctuations in the speed. You slowed down for a bump, slowed down for a moose. I don't know, right? Right? But anyway, I think that one's pretty clear. Scalar quantity and vector quantity. Well, we talked about them up here, didn't we? Scalar quantity is a quantity without a direction. A vector quantity is a quantity with a direction, right? So just to take another quick peek at this example over here, right? Distance, 7 kilometers, that's a scalar, right? Displacement, 5 kilometers, about 67 degrees east of north, that is a vector. Right? Average velocity, instantaneous velocity. Boy, that's not hard. Instantaneous anything is that quantity measured at a specific point in time, right? And it's found obviously with a tangent line, whereas an average is not found with a tangent line. An average is found by connecting 2 points on the line with sort of a straight kind of line of best fit. Actually, how's about I draw out, because we did mention vector tangent lines earlier, right? And Troy, I know that you don't have graph paper for what you're doing with these. So it can be difficult to draw out a proper tangent line. But like I said, I mean, boy, it's difficult to draw out a proper tangent line like any of the time, even with you know even with graph paper. Let's okay. So let's say the right. So say that was a graph of which we're looking at average velocity and instantaneous velocity. So this is going to be velocity, say meters per second. This is time in seconds. So the average, define the average between say here and here. What we're going to do is we're going to draw a line between those 2 points, like this, right? We're just going to connect it up, and the average velocity between those 2 points is going to be the slope of this line that connects the two, right? But say we wanted to find so that's going to be the average between that point and that point. But say we wanted instead to find the instantaneous velocity at this point here. What we're going to do to find the instantaneous velocity is draw a tangent line, right? So if you had to draw a tangent line for these ones, I understand that like this is a freehand one, so this is kind of analogous to the way you'll be doing it. Just sort of draw out the tangent so I know that you understand the method for what you had to do. You had to draw the tangent line like so, right? Right, so an average velocity uses kind of like a line of best fit to find the average in between there, right? Speed and velocity for 4D, we went over that kind of up here, right? But I will jot these ones down. So speed, right? Well, we went over that right there. Never mind. I don't need to do that one out. Right? That's right here. The rate of change of distance is your speed, right? The rate of change of your displacement is your velocity. Okay, so again, just like I was saying yesterday, that was I know it was a bit of an odd graph that I drew out yesterday and that I sent you after, but the point of showing that was that using the analogy of like a ball bouncing off the wall or something. If something bounces off a wall like that, generally we assume it to have the same force as it did when it hit the wall. I mean, some will be lost, of course, to various like friction and sound energy and all this kind of stuff. But generally, we say that the force that it comes back with is going to be roughly the same, or that's what we use for say some of the calculations that you'll see in later on. I'm not sure if that's your next course or one of the ones later, but the speed of the object before it bounces and after it bounces is the same, roughly, right? But the velocity changes distinctly, right? If it hits at an angle and bounces off like that, one component of the velocity might stay the same, but the other will change, right? Or if it bounces directly back at you in one dimension, like it hits a wall and then comes straight back, then the velocity is going to be totally opposite of what it was previously, right? Actually, yeah. How about I draw out something like that? Like say a ball travels like so, right? Comes down here, the ball hits the ground here like that, and then it bounces up this way, like so, and then keeps on going, right? Like that. Say that was what happened. Came in, hit the ground there, bounced up this way, right? The speed So the speed will be the same, right? Except for losses that are friction, air resistance, et cetera, right? But the velocity, right? So the velocity will be the same horizontally, but opposite vertically, right? Because the velocity on this side over here has a so has a downward component and a forward component. Whereas over here on this side, after it bounces, the velocity now has an upward component and a forward component, right? So you will see later on that you will use trigonometry, just like I showed in the previous short example, to calculate sort of the overall angle and the amount that it has vertical and the amount it has horizontal, right? But the speed here will be the same because the speed is just going to be this way and then this way, right? But these two will have same magnitude, therefore same speed, right? I hope that makes a bit of sense about these sort of quantities here, right? And distance and displacement, yeah, I think I may have beaten that one to death already. We might have gotten down through that one fairly decently, I think. Um, okay, rather than belabor this a ton, I think I'm going to skip on and do a few calculation questions. I think maybe 14 and 15 you were asked to do, and then hopefully that should be a good amount of prep to get ready for this test. Although Troy, if you're there in chat, you can at any point let me know if there's any other questions from the book that you would like me to go through on stream, and I will go through those here today. I have a little bit to get to for another student, but that student, like I mentioned in the intro, that student finished that course there today, so it's not super pressing for me to get to that. I just want to get to it at some point so I can send her the notes and video. But the stuff for students that are doing court tests tomorrow is obviously much more pressing to get to today on stream. Okay, I'm going to do question 14 here. Well, state officials in Hawaii are informed about a large earthquake detected near the Gulf of Alaska. Because earthquakes may produce a devastating tidal wave known as a tsunami, Hawaiians must be prepared to evacuate coastal areas. In one particular event, the displacement from the center of the earthquake to Hawaii was 2,235 kilometers south, and a relatively small wave arrived in Hawaii 3 3/4 hours after the earthquake occurred. Calculate the velocity of the wave. Okay, so we're only given a distance directly south, so our velocity will just be directly south, right? We're not having to fool around with finding the degrees like I did in the example because we're just given one component of the velocity, which is fine, or one component of the displacement rather, right? But we know that displacement is going to equal velocity over time. D equals v over t, right? Like this is maybe not the most basic, maybe the second most basic or second most fundamental of physics formulas after after the most important one, Newton's second law, F equals ma. Like literally the most important formula for physics. Um, Calculate the velocity of the wave, right? So it's just going to be, well, we know our velocity. Sorry, we don't know our velocity. We know our displacement, right? Or rather, right, v equals dt is the form we're going to need, of course. So we know our displacement is 2235 south, and we know that our time is 3.75 hours. Oh, I should have put km here. My goodness, my math teacher is showing. I'm not not writing in the units religiously all the time. I actually did do almost as many physics courses as math courses, so I really can't use that excuse. That was just a mistake. Um, so all we're going to do then is just velocity is going to equal 22. Wait, what am I doing? Well, you see here, this is meters per second. So I know that it was, what am I doing? What am I doing, Twitch chat? What am I doing? You know, sometimes you just got to take a step back and be like, hey, wait a minute. Hey, wait a minute. Maybe you're not quite writing it down correctly. You know, boy. Anyway, you know, we get there in the end, and that's my motto. As it turns out, as I wasn't quite sure that was going to be my motto when I started, but hey, you know, it is what it is, as you know, tautologies tell us. That's going to be 35 kilometers, right? That's going to be divided by 3.75 hours. So the velocity is just going to be, and there's a lot of beating around the bush just to get to this number, 596 kilometers per hour directly south, right? And to be very precise, we do keep our s in there because this is a, like I said, this is a vector quantity, so we do want to have the direction of our vector. Right? Comment on the size of the velocity. What method of transportation has velocity of this size? Well, they're looking for an aircraft there, obviously. 600 kilometers an hour, right? Either an aircraft or the Yami, that, or maybe, you know, the Vet, right? Drive from Toronto to Ohm, 1,400 road miles, made a trip in 13 and a half hours. Cops couldn't take it what they couldn't see, right? 1,800 road miles? You know, I've forgotten the quote. Oh my God, I can't believe I've forgotten the quote from a Buddy What's His Name bit. Anyway, you know, every time the piston goes down, you suck back a quart of gas. Oh, yes, my son. Using your answer to A, calculate the displacement of the wave in a time interval of 30 minutes. It's just mumbling. It's just rambling and nonsense. This is good content, right? This is obviously, this is the riveting stuff. Jeez. So we're looking for displacement. Displacement is equal to velocity times time, of course, despite what I might have written first. The displacement is just going to be 596 times 0.5, so it's going to be half of 596. Right? 596 was right up here, of course, because we have 3 sig figs. And the 0.5, they're telling us, oh, they're telling us 30.0 minutes. Right, so I could call this 0.500 because 30.0 minutes has 3 sig figs. So I'll just, even though I'm switching it to hours, I'm going to still have a value with 3 sig figs. So then we're going to have half of 596, which is going to be almost, which is going to be 2 less than 300, which should be 298. Yeah. 298 kilometers south. I say, putting my units back in the end sloppily. Whatever. Question 15. While sitting near the front of a bus, Andrew notices that it takes 21 seconds for the bus to accelerate from rest to 55 kilometers an hour north, and 12 seconds to slow down 55 kilometers an hour north to a complete stop at a traffic light. Convert 55 kilometers an hour north into a velocity in meters per second. Okay, well, what do? We get from kilometers per hour to meters per second. Going to divide by 3.6. So that's 55 divided by 3.6. Oh, 55 divided by 3.6. About 15.3. Right? It was 55. Yeah, we're just told 55 kilometers an hour, aren't we? We're not told 55.0. So we're going to have to make this guy a 2-digit. So that's about 15. meters per second. That's going to be 15 meters per second north still. Okay? Calculate the acceleration during the first 21 seconds. So it took 21 seconds for the bus to accelerate from rest to 55 kilometers an hour north. Well, it doesn't say what units to use for said acceleration, but I assume from part A that they want us to use meters per second, right? And anyway, kilometers per hour per second is a bit of an inelegant kind of unit. Meters per second squared, much more elegant, right? So it's just going to be, right? So we know that our acceleration is equal to our velocity divided by our time, because we need to go from meters per second to meters per second squared. So we need to get another meter down here, another second down here on the bottom, right? So our acceleration is going to be 15 meters per second divided by 21 seconds. It's going to be, acceleration is about 0.71 meters per second, or meters per second squared. What is the displacement of the bus at the end of the first 21 seconds? Okay. Displacement of the bus at the end of the first 21 seconds. Right. Notice it takes oh, we don't actually know that, do we? We don't actually know that unless we can say for sure that it's constant acceleration, can we? Right? But I guess we are to assume that it is constant acceleration. Hold on just a quick second there. Hold on just a quick second. I want to see the way that your but I guess we're tell you what. Let's go ahead and do this. Yeah, this is good. So, what do we have? Well, we have our velocity over here, right? So this is a velocity time graph. And then it increases. Takes 21 seconds for us to accelerate from rest to 55 kilometers an hour north, right? So in 21 seconds, so say this is 5, 10, 15, 20. So about 21 is going to be here, we'll say, right? And then it goes from that up to a velocity of 55, right? So this is velocity in, yeah, I'll keep it in meters per second, right? So our velocity is going to be in meters per second over here. So now we're going to have, what was the meters per second that it gets up to? 15, right. So 5, 10, 15. Yeah, I like showing it this way. This is good. So then we're going to go up here until it gets up to 15. There we go. So this is sort of a graph of the initial acceleration, like so, right? Now, it doesn't actually tell us that it's constant acceleration, but in order to solve this question, we are going to have to assume that it is constant acceleration, right? But now, once we know that this is our velocity time graph, well, what do we have to get to find the distance, right? Well, we know the distance on a velocity time graph is going to be the area under the graph, right? And the area here is, of course, going to be, this is a triangle, so it's going to be half times the time times the velocity, right? So we know that the distance, or the displacement rather, is going to be a half, right, times the well, yeah, it's going to be a half times the velocity, which is what it reaches up to, times the time, like so, right? And then this is, again, this is right, this is assuming that it was constant. If the acceleration was, say, like, if the acceleration was like this, right? Or if the acceleration was, say, like this, like that, well, then the area under our graph is going to be distinctly different, isn't it? So we don't actually know in these cases, right? But we have to assume then that the acceleration was constant, so that the rate of change of velocity was constant. But then, if indeed it is, then we can go ahead and calculate this, right? So we know that our displacement is going to be a half times the velocity which it gets up to, which is 15 meters per second, times the time, which is 21 seconds, like so. Right? So it's going to be then, displacement is going to be 7.5 times 21. Let's see. 0.5 times 15 times 21. It's going to be about 157.5. And we kind of have to round that to 2 because of our sig figs, right? So we say z is equal to 160 meters, right, to 2 sig figs, like so. Yes, okay. So this is the way that we would go about doing these ones. Now, again, right, I am going to quibble a little bit here because it should have said that the acceleration was constant here in order for us to know. Because, right, the red line or the green line or any number of other lines that like are jagged and up and down and all over the place would still fill the requirement of the vehicle accelerating from rest to 21. But as we notice, like in the green case, the area under the line is a lot smaller. In the red case, the area under the line is a lot bigger, right? Or either way, right? Equals 160 meters. Calculate the acceleration during the last 12 seconds. How does acceleration compare with the initial acceleration calculated in B? Well, 12 seconds to slow down from 55 kilometers an hour north to a complete stop, or in other words, from 15 meters per second north, right? So again, um, we want acceleration. Acceleration is going to be velocity divided by time. Acceleration is going to be now it's going to be a negative 15 meters per second, just to show you, right? Because we can either call it a negative 15 meters per second north, or we could say 15 meters per second south, right? In a sense, but for my money, it makes more sense to say negative 15 north because it's sort of like slowing down in the north direction, right? We'll divide that by the time of 21 seconds. Sorry, it's not 21 seconds. Never mind. No, it's 12 seconds this time. 12 seconds. So the acceleration is then going to be, I should know 15 over 12 off the top of my head probably. 1.25. That is 12 seconds. Yeah, so it's going to need to be negative 1.25, or would say negative 1.3 meters per second squared in, right? Because it's 2 sig figs. You don't necessarily need to write in that 2 sig figs bit. I just wanted to put that in there so it kind of makes sense to somebody who is reading it afterwards to see. All right, I will label this part over here as being, what was this, 15C over there. Okay. Yeah, that's been a fair bit looking at this course there. Troy, I hope that was somewhat useful for you to show some of the calculations and some of the terms that we're going to be using. Like I said, if you've got any questions, do please let me know. I know we're rapidly running out of time for getting more examples done, but if you say if you're watching the stream or Even if you like email me something in the next few minutes, I will try to get that done as quickly as possible. And of course, I can do examples off stream too and send you those, right? Just write it up. So if you've got any questions while you're reviewing or preparing for the test, just let me know and I will get to those as best I can. Okay, but for now, then I have one more short topic to get to. That's going to be a few questions for Calais from a activity that she did just today. So let's bounce back over here now to the document display. Here we go. Let me change my background. Yeah, I'll use this one. This is a very colorful, springy one. I haven't used this one yet at all. This is a picture from I mean, just a very cropped picture. I mean, it could be basically anywhere. So that was from my grandparents. I mean, now it's a cottage, but previously it was like a childhood home for my grandmother, I believe. Anyway, it's in Point of Bay, or was before they got rid of it. Anyway, this is Math 3101A, and this is going to be just a review, sort of an overall review. I'm going to do questions 9, 13, and 27 off of this activity. So question 9 then. Yeah, let me zoom in a little. How many ways can the letters in the word factor be arranged if you must start with a consonant, factor, and end with a vowel, ao? All right, good. Good. They specified that, so it's not an English quiz by any stretch of the imagination, because they specified what the letters are. So what is the situation that we've got here? Well, we've got a 6-letter word, F-A-C-T-O-R, like that. If you must start with a consonant and end with a vowel. Okay. So we know that we can go ahead and sort of fill in what goes where. This is going to be a little odd, but because it's a small bit different than some of the previous ones that we've done, but I think it'll make total sense as we go through. Right? So there's 4 possibilities for this letter here, right? Because that letter has to be a consonant. So there's only 4 possibilities there. This last one here, this one has to be a vowel. So there's 2 possibilities there. Right? Then what's left over for these middle guys here? How many letters are left over? Well, there's 1 consonant gone to take account of this one here. There's 1 vowel gone to take account of this one here. So we've got 4 letters left in total. So out of those 4 letters, we have 4 options here, 3 here, 2 here, and just 1 left over here. Right? I know it looks odd to have it ending at a 1 here and then back up to a 2 there, but I think you see as I'm talking through why that makes sense. Then we're just going to go ahead and multiply all those guys together. Which is going to be 12 times 4 is 48. 48 times 2 is 96. 96 times 2 is going to be option C, 192. Or option C. Right? That's all we got to do. That's all we got to do for that one. I know that setting it up there is a little bit different than some of the ones you might have seen already. But I think, like I said, talking down through the reasoning of it, it does make sense. I know it seems a little bit mean sometimes for like an activity like this to pop one on you that you haven't quite seen before. But the point is to make sure that the students are understanding sort of the reasoning behind this and why these questions work. And I think, like I just talked through there, conceptually, this question makes a lot of sense. Number 13, I'm going to do next. So John, Sam, Alice, and Brianna are to be arranged in a line from left to right. How many ways can they be arranged? Well, yeah, this is a relatively straightforward one, right? Like, there's 4 people, right? And obviously the same person can't be in 2 different places. And an order, obviously, it's different. It's not just one order, right? It's not just choose the 4 of them. Obviously, it's permutations. I mean, you could say it's 4p4. You totally could say that. And that would work. It would get you the right answer. You could also say that it's just 4 factorial. right? Because there's 4 people for the first spot, 3 there, 2 there, and 1 there. 4 times 3 is 12, 12 times 2, 24. So that's going to be option D, there like so. I know those two were very quick questions. The main one that I wanted to get onto was number 27, which is down here. All right. So this question here, this is, I'd say, in this course, this is probably one of the questions that am asked about most. Honestly, like this, it's a relatively tricky in a sense because it's the same sort of error. That's not Kelly. It's totally not your fault at all. Rather, what I'm saying is like this is the one that people very commonly struggle with, but it's always just one small thing. It's always just the same one small thing. Let me go back over to this one so I get a bit more room to show you on the page here. But let's start doing out our Venn diagram. So this is customers at a movie theater were surveyed about the number of movies that they like, or the types of movies that they like. This is going to be question 27. All right, so let's start writing down in set notation what we know. Right? We know that 25 liked horror movies, so the number of horror fans is going to be 27. All right, we're also told the number total, right? I should have put that at the top. We're told the number of total is 50, right? So we know that if we add these guys, add all these areas up, and we're getting more than 50, we know we did something wrong, right? The number of horror is 27. The number of sci-fi is 23. The number of comedy is going to be 21. The number of all three. Okay, so it skips down to talking about all three here now. But this is the number of horror and sci-fi and comedy. That's going to be 3. The number of horror and sci-fi is going to be 14. The number of sci-fi and comedy is going to be 7. And 4 didn't like any of the 3 types of movies. So how can we write that in set notation? Well, what we can call that is the number of not horror and not sci-fi and not comedy. That's going to be 4. Okay? So then, let me just tell you what. Let me just draw a line over here to bracket off these previous 2 questions. So when you're looking at it afterwards, you can see pretty clearly that the rest of the stuff on the page here is about question 27, because I'm going to need a bit more room to get to this guy. All right, what does this now tell us about the way our Venn diagram is going to look? Let's draw this one out like so. So I'm going to have horror over here, and I'll keep using my different colors for these ones. Horror over here, sci-fi over here, and we're going to do comedy down here. Okay? What do we have for all 3? Right? Because like I said, when we're filling in a Venn diagram like this, we always start in the middle. Always start in as close to the middle as we can. Right? So what's the number of horror and sci-fi and comedy? Well, that's a 3. Right? So we know that a 3 goes down here. Okay? So next up, we're told that the number of horror and sci-fi, so horror and sci-fi, that's 14. So does that mean I put a 14 here? Did I just go and stick a... No, I don't. I don't go and stick a 14 in here. Right? Why don't I? Well, because this area, just this area here that I'm re-outlining, this one here, that section there, that is not the horror and sci-fi section. No, it's not. The whole circle here, this whole bit counting the 3, is the horror and sci-fi section. This one is what we would call horror and sci-fi. This one over here, right, would be number of horror and sci-fi and not comedy would be this section. But we're not told that, right? But to get that, what we have to do is the number of horror and sci-fi subtract the number of horror and sci-fi and comedy. So that's going to be 14 minus 3, which is going to be 11. So we know that the number that goes over here is 11. Right? And that's perhaps the single most common error, the single most common type of error that we see in this whole course, I would say. Right? It's a very easy mistake to make, especially when you're not consciously thinking, hey, I should be looking out for this. But that's exactly what you have to do here. And by the same token, then, the number of sci-fi and comedy, well, that's this full circle down here. So the number of sci-fi and comedy is 7, which means this part out here has got to be 4. Now I think you're starting to see what we got to do, right? To find the number of sci-fi and not comedy and not horror, that's going to be the number of sci-fi minus these other ones, minus 11, minus 3, and minus 4. I'm running out of a bit of space here because I'm really doing a long-winded sort of take on this one. So I'm going to clue up some of the working a little bit here. But it's going to be 23 minus 18, which is, of course, going to be 5. Right? Because from this here, we know that all the values in the sci-fi section got to add to 23. These ones here add to 18. So that means there's 5 left over for out here. Now, how are we going to go about finding these other ones over here, this side? Well, we don't know. We don't know what's in here, do we? We don't know what's in that one. And that one's in between. That one's shared between those two guys. So we're going to have to call that one X. Right? And then we're going to know that over here in H, well, that's going to be 27 minus 11 minus 3 and minus X. Or in other words, it's going to be 27 minus 14 is going to be 13. So that's 13 minus X. So whatever X is, whatever's shared between these two, this one's 13 minus that amount. This one over here, comedy, is going to be 21 minus 3 minus 4 minus X, which is going to be 21 minus 7 is 14, so it's going to be 14 minus X. And we know from this one, we were told that guy, there's a 4 out here. Right? So now armed with that knowledge, we can go ahead and finish the question. Okay, so because we know that the total is 50, so we know that 50 is going to equal, then all of these places added together are going to make 50. So it's going to be 13 minus X plus 11 plus 5 plus X plus 3 plus 4 plus 14 minus X, like so. Right? So we know that 50 then is going to equal, let me just go ahead and put this down, 13 plus 11 plus 5 plus 3 plus 4 plus 14. Oh, right, and then plus the 4 on the outside. Right. Right, I almost messed that one up. Right, because we've got our 13 minus X, which is this one, our 11, which is this one, our 5, which is here, X, which is there, 3 is there, 4 is there, 14 minus X is there, and then the 4 on the outside. That one was extreme. All of the numbers are important. Go figure, right? Like all of them. You got to write down a lot of them. So it's going to be 13 plus 11 plus 5 plus 3 plus 4 plus 14 plus 4, which is going to be 54. And then here we've got 2 X's, 2 negative X's, and 1 positive X. So it's going to make 1 negative X. 50 equals 54 minus X. I think you see where we're going with this now. Right? X is equal to 54 minus 50. X is equal to 4. Now once we know that, so that X is equal to 4, we know that there should be a 4 in here. Right? There should be a 10 in here. And there should be a 9 in here. Draw a Venn diagram in terms of the number of people who liked horror and comedy, but not sci-fi. Right? So we were asked to draw out the Venn diagram, but then our answer is going to be 4 people. Or in other words, the number of horror and comedy and not sci-fi equals 4. Right? There we go. So that's all. Yeah. That is similar to ones that you've seen already. I think that's a fairly good look at the way you will solve these questions, right? Anyway, that is going to be all for me for today, I think. Let's go back over to my intro screen. I did get to everything that I wanted to talk about today. Rambled a bit about physics. It's kind of fun. Introduced some stuff for Troy's next course as well as the current one. Calais, hopefully that was a good review of that, so you can understand sort of where the grade came from on the activity that you had. Right, and I do have, I have quite a bit going on this afternoon and tomorrow further on for teacherly duties, right? So I am going to go and take care of some of those here now. Thanks very much for being with me again today, folks. It's been a pleasure as always to be here. Helping during social distancing, helping people keep on top of things and get their work done, right? Guess this will be maybe this will be the last time signing off in this way, but I hope you stay safe, and I will see you again tomorrow.